Okay.
Okay, good afternoon. This is Randy Zimmerman. I'm going to be your instructor today. We're going to talk about terminal unit technology. Now, I've been at Titus for 38 years, mostly working around terminal units, and I serve on all of the committees at AHRI and ASHRAE that write the standards for terminal units. So we've got a number of topics we're going to talk about today. First of all, we're going to start out looking at types and applications. We'll look at single duct terminals, very briefly at dual duct terminals. We'll also look at exhaust boxes. Then we'll get into the series fan powered and parallel fan powered terminal units. Then we'll take a look at some selection and sizing issues involving inlet ducts, fans, electric coils, and hot water coils. And finally, we'll end up with a few recommendations for ideal installations for terminal units. So we'll get started here with types and applications. And of course, the most basic terminal unit would be your single duct VAV box. If you look at this cutaway picture here, you can see the structure of the unit. It's got the round inlet with a flow sensor in it so that the control system, which is hopefully going to be pressure independent, can actually monitor the inlet velocity of the terminal unit and then allow the controller to automatically adjust the damper position to deliver the desired CFM, and automatically correct for changes in inlet pressure. You'll notice that the configuration of this unit has a round inlet and a rectangular outlet, and that's not by accident. When Titus pioneered this type of a design back in the 1970s, we always tried to make the discharge connection at least twice the cross-sectional area of the inlet. And the idea there is that as air flows over the damper and then expands to fill the casing of the unit, we get some static pressure regain in there, and that lowers our static pressure requirement to the room. Of course, we also know that the round inlet is the most efficient way to deliver air to a room. Like I always say, air is round. You can put it into a rectangular inlet, but then it just goes oval shaped. So we want to have a round inlet. We want to have that rectangular discharge. The rectangular discharge is also the most convenient for connecting our field fabricated duct runouts, where we're going to have our takeoffs for our diffusers and our balancing dampers, and then connect our flex duct and then our diffusers. Now, of course, our single duct VAV box is the most common type of box, and a unit without a coil on it would generally be used for controlling interior spaces. So it typically receives 55-degree air from the air handler, and then we use that that airflow from the air handler is going to provide our ventilation to the space. We need to meet the ventilation requirements of ASHRAE standard 62.1 to make sure that we have adequate ventilation for our occupants. And the box is going to generally modulate between two preset flow rates. That would be our design cooling CFM and our minimum ventilation CFM. And then the damper is going to move in response to a wall-mounted room sensor to maintain room temperature while staying between those preset minimum and maximum flow rates. Now we can take that same box and we can set the minimum and maximum airflow rates to the same value, and it becomes a constant volume box. Now, of course, if we're going to do a constant volume box, we can't control room temperature that way. So we would have to put some kind of a coil on the box so that if we can't control the room temperature with air volume, then we're going to have to do it with air temperature. So then we would be taking our 55-degree air from the air handler and reheating it in order to maintain temperature control in the room. And of course, constant volume boxes like that would typically be used for critical environment spaces, like doing room pressurization, for instance. If we want to build a positive or negative pressure in a laboratory or a hospital room, if we put the room under positive pressure, it becomes a protective environment for whatever we've got in the room because we're going to have positive pressure pushing out on the walls. Or we can create an isolation ward where we keep the room under negative pressure, and that holds whatever's in the room so that it doesn't contaminate surrounding spaces. So that would be like a patient with a highly contagious disease or something like that. And of course, we're going to have to get the right number of air changes per hour in order to meet the requirements of ASHRAE standard 170, which is the healthcare standard. Now, when we put reheat on a box, a single duct box, it's important to know that we have to have at least 3 different flow rates there. We still have our cooling design airflow. We still have our minimum ventilation airflow, but then it's nice to have a heating flow rate so that the box can move, let's say, from 100% cooling down to maybe 15 or 20% ventilation, then maybe open back up to 50% to get some more air through the coil for doing our heating of the space. And of course, that would be typically used for either constant volume rooms or perimeter rooms where we're doing VAV and we have to counter the loads from glass and exterior walls. Now here's a sequence that's little understood by people, and that's auto changeover. Let's say that we've got VAV boxes in a small tenant space, and that tenant space maybe has a rooftop unit, and that rooftop unit can provide cooling, but also has central heat in it, maybe gas-fired heat. So that would be like a small lease space in an office park or something like that. And if we put VAV boxes in that room, or so inside that suite, then the boxes need to know whether the air handler is in heating or cooling. So that typically involves putting some kind of an inlet mounted temperature sensor on the box, so that the box knows whether the supply air temperature is warmer or cooler than the room temperature that we're trying to control. That allows the box to know whether it should be opening or closing to counter changes in room conditions. So that's auto changeover. Now, with digital controls, we don't necessarily have to have that inlet mounted sensor. The air handler could shoot out a signal, like a global command out to all the boxes telling them whether they're in heating, ventilation, or cooling mode. But of course, in these smaller buildings and smaller systems, that digital control system is rarely going to be set up to do anything like that. So we're back to having an inlet mounted sensor on each box to tell that box's controller what the supply air temperature actually is. Now, exhaust terminals. Exhaust terminals are used typically in critical environment spaces, just like where we would use that constant volume VAV box, because if we're going to try to control the pressurization in the room, then we've got to be able to control the air flowing into the room from the supply box, but also control the air flowing out of the room with an exhaust box. So like we said before, positive pressure creates the protective environment, negative room pressure creates an isolation room. Typically, the way this is done, the supply box handles constant volume with reheat, and then this exhaust box usually maintains a set offset in airflow control to either be slightly higher or slightly lower than the supply volume to create that negative or positive pressure in the room. The important thing is we actually, if you go back and look, we've got 2 examples of exhaust boxes here. We've got a round inlet, round outlet, and we've got a rectangular inlet, rectangular outlet unit shown there. It just kind of depends on what your ductwork configuration looks like as to which box you'd prefer to use as an exhaust. What you don't want to use is a supply box as an exhaust box. Now, I should say it's been done a million times and people get away with it a lot, but it's just not a good idea, because if you hand the same box for supply and exhaust to a contractor, the contractor in all likelihood knows exactly how to install a supply box because they do that all the time. But if you hand them that same box and tell them it's an exhaust box, there's going to be a tendency to go, let's see, exhaust. I need to flip this box around backwards and put the rectangular discharge facing towards the room and the round inlet duct facing the exhaust fan. And that creates problems because that puts the flow sensor on the wrong side of the damper, and it has the flow sensor pointing in the wrong direction. Now, I often get calls on these afterwards where people say, gee, how do I fix that? We just installed 50 of these backwards. And of course, they got no room to redo the ductwork. And the usual solution is to remove the sensor, flip it around the right way, and put it further downstream in the ductwork to get it away from the influence of the damper. Likewise, you can also get a retrofit sensor assembly from us and mount that further downstream in the ductwork. But just to avoid all those problems, it's better just to get the proper box. And I will say that even if you install this box correctly with the inlet facing the room, that static pressure regain that the unit is designed to create in the supply mode will actually work against you in the exhaust mode and create more work for the exhaust fan to overcome. And then, of course, if you flip this box around backwards, you're creating a configuration that's very non-aerodynamic and will create a lot more noise and a lot more pressure drop than you would get from a standard exhaust box. So the best thing is just avoid it, use the correct exhaust box. Now, I'm not going to spend much time talking about dual duct boxes. Dual duct boxes are used when we're mixing hot and cold air together. And I usually joke around and say that, where do you find dual duct boxes? Usually you find them at universities, you find them at hospitals, and you find them at university hospitals. They're usually, used anywhere where people want to centralize their equipment, so that they usually are only found in institutional work. There probably hasn't been an office building built in North America using dual duct boxes since the 1970s. And sometimes people are confused by why there's so many different models. It's based on the type of mixing they provide. If you just take two single duct boxes and screw them together, that's a non-mixing box. That means they're not designed for mixing hot and cold air together. One damper is going to be closed while the other one modulates. So that's your heating or your cooling box. Then you got the standard mixing box that gives you a 1:10 mixing ratio, which is standard in the industry. And then some really fussy universities want a 1:20 mixing ratio and will opt for the high mixing box, which is physically larger and more costly. Now let's jump into fan-powered terminals here because I think there's a lot more interest in these products. Now, there are lots of different models of fan-powered terminal units available, all different configurations, standard configuration, quiet configuration, low profile. I've even seen some low temperature units. There's underfloor units, all different types of units, but they all basically fall into two families. They are either series fan-powered boxes or they're parallel fan-powered boxes. And if we look at this cutaway of a series fan-powered box, you're going to see that they're pretty much defined by the location of the motor blower inside the unit. So if you look at this cutaway of a series fan-powered box, you'll see that the motor and blower is located at the discharge of the unit. Then on the inlet panel, you've got a round inlet that's going to take cold air from the air handler, and it's got a flow sensor and a damper in it, just like a single duct VAV box. Then you've got that big rectangular opening there called an induction port or a plenum inlet, some people call it. And so we're going to get cold air from the air handler, and that's going to modulate the primary air based on a room sensor down on the wall of the room. And as the primary inlet closes, the fan is going to draw an increasing amount of airflow through that plenum inlet to make up for a lack of primary airflow. So you can think of fan-powered boxes like this as drawing in warm return air and mixing it with the primary air, because all of the air going out to the room is going to go through the blower. And that's important to note, because if the blower in this fan-powered unit, the series fan-powered unit, is not running, there's no way to move primary air to the room. If the blower is not running, it's almost impossible to blow primary air through the pressure drop created by that dead blower. So what will happen is the primary air will simply follow the path of least resistance and do a U-turn and head right out the induction port. And that leads to some funny phone calls that I take. You know, somebody will say, I think my blower's running backwards. And I'll say, what makes you think your blower's running backwards? And they go, well, we can't keep the filter on the induction port. And my next question is, why are you running the box with a filter on it? And then they say, well, it came with a filter, so we thought we had to keep putting filters on it. I said, well, the news is, you know, the fact is most fan-powered boxes run without filters. Usually filters are used to protect the motor and blower from dust contamination during construction, but usually during the balancing and commissioning phase, that filter is usually thrown away. But also I should say that if that blower were running backwards, it would still be moving about 50% of the rated airflow to the room. It's not going to blow the filter off. If the filter's being blown off, it's because you have excess primary air dumping out through the induction port that could be blowing the filter off. Now, on a series fan-powered box, the fan runs all day long and then simply turns off at night and on weekends. But the fan is also free to come back on during nights and weekends. And that's one of the things people really like about fan-powered terminal units. You can maintain night setback conditions on nights and weekends without running the air handler, because the fan box has its own source of airflow. It's also important to show that you can duct that induction port back to a return air grill in the room if you need to. You do need to try to keep the pressure drop on that ductwork as low as possible. And of course, in healthcare applications where you're not allowed to share return air between two spaces, you are required to duct that induction port back to the patient room. Now, another thing about series fan-powered boxes is they have very low inlet pressure requirements, because the air handler only has to move air to the box, and then the fan on this unit picks up the air and moves it the rest of the way to the room. So you can think of this as being like a booster for the air handler. Series fan-powered boxes can actually run with inlet pressures as low as ½ an inch, as opposed to the inch or inch and a half that you might be using for other types of VAV boxes. So series boxes and parallel boxes each have their advantages and disadvantages. The advantages of the series fan-powered box would be that you get constant air motion in the room because you got that constant discharge from the fan. That's going to give you more room air mixing, should make the space feel fresher because you're getting more air motion, more air changes. You're also getting a constant sound level from the fan. And many manufacturers of series fan boxes offer noise reduction packages to reduce the sound level of that fan. You've also got the reduced inlet pressure we discussed earlier. Now, the disadvantages of the series fan box would be, hey, the fan's got to run all day long, and the fan has to be large enough to handle the cooling design airflow. So the fan in a series fan box could be twice as large as the fan in a parallel fan box. But let's look at that parallel fan box. And you can see here in the cutaway, the motor blower assembly is set back inside the unit on a parallel fan box, and the fan only runs during the heating mode. During the cooling mode, the fan is off, and the primary air valve is simply conditioning the space just like a single duct VAV box. Then as you have less cooling demand in the space, the primary damper closes down to a minimum ventilation flow rate just to provide ventilation to the room. And if the room temperature continues to drop, then the fan kicks on to pull that warm return air from the ceiling plenum and move it out to the room. And of course, this is a parallel fan box because the primary airflow is moving in parallel to the fan airflow. The primary airflow goes around the blower and out to the room. The return air goes through the blower, mixes with the primary air, and goes out to the room. Now you'll notice there's a backdraft damper on that fan. And that's critical because when the fan's not running during the cooling mode, you don't want your primary air to dump out that induction port. So you've got usually a gravity operated backdraft damper that flops down and closes off the discharge to the fan to block that primary airflow. Now, of course, this type of box is going to take you back to the higher inlet pressures like you'd have for a single duct VAV box. But let's look at the advantages and disadvantages. Now, the advantages would be that the fan only has to be big enough to handle the heating flow rate. So it could be half the size of the blower in a series fan box. And the fan's only going to run during the heating mode. That makes these units very quiet during the cooling mode. The disadvantages would be the modulating sound level. That's one thing that some engineers don't like about parallel fan boxes. They've got multiple sound levels. There's one sound level at maximum cooling. There's one sound level at minimum cooling. And then the sound, of course, jumps up when that fan turns on. So you've got different sound levels to deal with. You've also got that higher inlet pressure requirement, like 1 or 1.5 inches, as opposed to the ½ inch you might be able to get away with a series fan box. And you've also got to deal with varying airflows on our diffusers. So when you're selecting your diffusers, you've got to select them such that they can deal with VAV turn down, which can be problematical for certain types of diffusers. If you're using a high quality, high performance diffuser like a Titus TMS, that's a multi-cone diffuser, or a Titus Omni, that's a plaque diffuser, those can deal with about an 85% turn down very comfortably. Whereas if you got a low quality, low performance diffuser like a perforated face diffuser, those diffusers with a turn down of less than 15% can actually start to drop their air pattern off the ceiling. And that some people refer to that as dumping. I prefer to refer to that as excessive vertical projection because it just sounds a little more scientific. Now, the other thing that we have to be conscious of when we're dealing with parallel fan boxes is air leakage. Air leakage can be a big problem on some parallel fan boxes, and the higher your discharge pressure is, the more the parallel fan box is going to leak. If you look at the series fan box, if it's set up and balanced properly, any leakage would leak into the box because the cabinet on a series fan box shifts between a neutral pressure to a slightly negative pressure. So it draws air inward. On a parallel fan box in the cooling mode, a large portion of the fan cabinet is under positive pressure. And if you've got access doors to get into the motor blower assembly and lots of wiring knockouts and wiring pass-throughs for the fan motor and the controls, there are numerous places where parallel fan boxes can leak. We try to design our fan boxes for no more than 10% leakage. That would be worst case. But believe me, I've seen some instances where parallel fan box leakages can be a big issue. Now, there was an ASHRAE research project that was commissioned many years ago called ASHRAE Research Project, RP 1292. And the purpose of this research project was to look at the series and parallel fan box and determine which one was more efficient from a whole building standpoint. So 3 manufacturers provided small and large series and parallel boxes to Texas A&M, and they built a computer model of a building and then thoroughly tested these boxes for every aspect of energy usage. Then they could drop them into this computer model and look at the building energy picture. Now, the building could be dropped into different climate zones. Like I know that it had San Francisco and Chicago and Houston and Boston. And it could also be operated on different time of day schedules. Now, if you look at that 400-page report and you cut to the chase and go to the end and see, well, which one is more efficient? The answer was, it depends. If you properly size and select these boxes, you could get equal results with a both series or parallel unit. Now, unfortunately, when this project was conceived, most fan-powered units were using PSC fan motors. Those are permanent split capacitor fan motors. But by the time the project was ended, ECM technology was really getting a major foothold in the industry, and that's what people were more interested in. So a group of concerned people got together and pooled their money, several manufacturers, and they had new samples sent to Texas A&M with ECM. That's the newer programmable motor technology. They reran the project and issued a privately issued report, which ASHRAE won't publish because it was not done under their auspices, but it is available through places like AHRI because all of the research was donated to industry. And I've got a copy of the report also. And basically it showed that when you went to the newer ECM motors, they greatly improved the efficiency of the series unit because the series unit could take more advantage of the high efficiency of the ECM. And so as far as I'm concerned, the ECM is now the state of the art. Excuse me, I should say the series unit with ECM is the state of the art. And of course now energy codes are stating that you have to have a minimum fan efficiency of at least 70% in any product where the fan runs during the cooling mode. And although they can't require you to use ECM, that's the only technology that will give you that kind of efficiency. So in many places, you must provide series fan units with the ECM. But in those same markets, you can still use the parallel unit with the PSC motor because the motor only runs during the heating mode. Unfortunately, that is pushing some customers to switch from series to parallel so that they can use the less costly but much less efficient PSC motor. So to me, it's a bit of false economy because you're trying to dodge modern technology, which is more efficient, for a short-term reduction in first cost, whereas you're probably going to be paying for that first cost through lower efficiency for the life of the building. So I'm not a big fan of that. Now let's take a look at sizing and selecting. I've got some golden rules that I use for selecting box inlets. And the first thing is when I'm doing a VAV inlet, I try to size the inlet for as close to 2,000 feet per minute inlet velocity. Because I know if I do that, it's going to prevent me from oversizing the inlet, oversizing my ductwork. And it's also going to give me a very comfortable VAV turn down of 85% without losing my accuracy on my flow control. Now, if I'm doing a constant volume terminal, I've got a much wider selection range of 1,000 to 2,000 feet per minute because there's no VAV turn down to consider. Now, if you look at these two fan curves, you're going to see a PSC fan curve looks very different from an ECM fan curve. The PSC fan curve, we've got a maximum curve, and then we've got a 1-row curve and a 2-row coil curve. Then we've got a minimum curve. And that minimum curve is the 600 RPM curve for the PSC motor. You never want to go below that minimum curve because below 600 RPM, PSC motors with their sleeve bearings don't properly lubricate, and you rapidly get rapid wear on your bearings and overheated fan motors. And so you want to stay away from that curve. The ECM is very different. You can see it's very flat from over much of its operating curve because it's programmable, and most people program their ECMs to automatically compensate for changes in external pressure. So they do compensate up to a certain point at which they start to run out of horsepower, and then the curve noses over. ECMs don't really have a minimum curve, but most manufacturers program a minimum speed curve into their motors to prevent them from getting into situations where the motor may have trouble stabilizing, where it runs roughly at the low end. So we try to program a minimum curve that allows the motor to run smoothly. Now, when I'm selecting PSC fans, you know, most people select with a discharge pressure assumed to be 0.25 inches. That seems to be kind of standard in the industry. I actually have found that discharge pressures are usually much lower than 0.25 because people tend to over-engineer their discharge ductwork. But if we just stick with the standard 0.25 selection point, I try to select in the top 25% of a PSC fan motor curve because I know that I get my highest efficiency and cooler running motor up at the top end of the curve, and that's going to make the motor last longer, run cooler, and run more efficiently. Now, ECMs are a totally different game when you're selecting them. They don't burn up at the low end, and actually ECMs have a minimum efficiency of 70 or 80%, depending on who you talk to. But you find that if you turn the speed control down on an ECM, the efficiency actually increases. So it's not hard to get efficiencies up in the 90s, 95, 96% efficiency as you turn the speed down. So I tend to select my ECMs in the lower 50% of their range so that I get a quieter motor and get the highest possible efficiency. I don't have to worry about burning up an ECM because they have ball bearings and don't have the low speed operating issues associated with the PSC motor. Now here's a problem that sometimes people run into where they select a PSC fan low. They'll select it at 0.25 inches and they'll say, hey, I'm on the safe side of that minimum operating curve. But then when the box actually gets installed and the operating pressure isn't really 0.25, let's say it's really less than 0.1, that can shift your operating point to the wrong side of the curve, and now you do have an operating problem. So that's why you never want to select PSC motors anywhere close to that curve, because there's always the danger that the actual operating conditions could shift you to the bad side of the curve. Now, just briefly about electric coils, we always want to keep our discharge temperatures as low as possible. UL sets a maximum discharge temperature for any electric duct heater is limited to 120 degrees. That's why they have us put 115 degree auto reset thermal cutouts to hopefully try to prevent it from ever going over 120 degrees. But of course, we don't really want to discharge at 120 degrees. ASHRAE recommends that for overhead diffusers, you should never discharge at more than 15 degrees above the desired room temperature. And that's to try to prevent try to encourage good room temperature mixing to get consistent floor to ceiling temperatures and prevent temperature stratification, which could cause thermal comfort issues in the space. So we want to keep our overhead heating temperatures as low as possible. Most people try not to go over 90 degrees. Now for hot water coils, lots of people have trouble selecting coils because they can't get an exact match to the schedule they've been handed. And usually it's impossible to get an exact match unless you are the basis of design. You know, basically the key here is to try to select a coil that meets or exceeds the desired capacity or leaving air temperature without exceeding the maximum water flow by too much. And then just kind of keep an eye on the water pressure drops. Now, most people are going to try to avoid 3 and 4 row coils. So usually the question comes down to, do I need a 1 row coil or do I need a 2 row coil? Now, one big problem that we see is low water flow. Sometimes I see people selecting multi-row coils on large units with fractional GPM water flows. And that's a problem because the water's got to be moving through the coil if you actually want to get some heat transfer. Now, our coil selection program allows you selections in turbulent flow conditions down through the top 50% of transitional flow. Once you get into the bottom 50% of transitional flow, that's where the coefficient of heat transfer takes a nosedive, and it's almost impossible to predict exactly where that's going to happen. And of course, you know, the type of flow we've got is going to be determined by the Reynolds number, which is a function of the water velocity and viscosity of the liquid we're dealing with. So the minimum recommended GPM is affected by the entering water temperature, the altitude of the job site, and the glycol concentration of our fluid. So hopefully you're dealing with selection software that gives you a warning, because if you drop below the minimum recommended GPM, a program is going to probably overpredict the capacity. It's not going to be the correct capacity. It's going to overpredict. So you don't want to go anywhere near the minimum GPM because if you select at the minimum GPM, you're probably going to have poor valve authority on your control valve. Now, another thing we run into, you know, most of the coils in this industry were designed for an entering water temperature of 180 degrees because that was the standard for so long. But now people are using the newer condensing boilers, which tend to run most efficiently somewhere between 110 and 120 degrees. And of course, we have the same heating requirements we've ever had. So if we want to deliver the same heat, but we got lower entering water temperatures, something's got to change. And some manufacturers offer the option, instead of a standard 10 fin per inch coil, they may offer an optional 12 fin per inch coil and call that a high performance coil. I just call that a 12 fin per inch coil because that's what it actually is. Actually, the best solution for dealing with lower entering water temperatures is an option that we've added on our single duct boxes some time ago, and that's called the enlarged casing option. Like on a single duct VAV, that basically allows you to have like an 8-inch inlet on a 10-inch unit casing with a size 10 water coil. So it upsizes the water coil by 1 cabinet size for the inlet duct on the box. That gives you more thin area, which is the best way to increase our capacity because we're getting to use a standard coil. We don't have to increase our fin count. We don't have to do anything fancy. We're just going to upsize the casing to put a larger coil on a smaller inlet duct. It's the most efficient way to get back to the capacity we need without increasing the number of rows, without increasing the air pressure drop. It's just the best way to do it. Now, here's some pointers for ideal terminal unit installation. First off, we want to size our inlet duct for no more than 2,000 feet per minute. It would be a good idea to have at least 3 equivalent duct diameters of straight duct approach, although we say that we can deliver catalog performance with our boxes and our inlet sensors with only 1.5 equivalent duct diameters of straight approach. Then we want to put the box as high above the ceiling as possible, and we want to have a ceiling if at all possible, because a ceiling helps to block quite a bit of noise. Sometimes I get asked about spring isolators. Spring isolators aren't absolutely necessary to good terminal unit performance. The boxes are actually tested, hung rigidly. That doesn't mean the spring isolator won't provide good insurance for unforeseen job site conditions. So they're still a good idea. They're just not absolutely necessary. Sometimes it's a good idea, especially on fan-powered boxes, to provide flexible connectors at the inlet and the outlet to break up any duct or terminal unit vibration. Then it's a good idea to have at least 4 feet of line duct before your first diffuser takeoff. Then it's a good idea to size that discharge duct for no more than 1,000 feet per minute. So I always think of terminal units as cutting velocity in half. 2,000 feet per minute on the inlet, no more than 1,000 feet per minute at the discharge, and then use a good quality lined flex duct to eliminate a lot of discharge sound from a terminal unit. Some people call lined flex duct flexible silencer. Just because it comes in a 25-foot piece doesn't mean you have to use the whole thing. They actually make tools for cutting it. You don't have to tie it in knots and shove it above the ceiling. So hopefully I've covered everything I wanted to cover here. You want to use the correct terminals for exhaust. You want to use series fan powered with ECM because that's really the state-of-the-art fan-powered terminal unit. You want to size VAV inlets for no more than 2,000 feet per minute. You want to select PSC fans in the top 75% of their operating range. Should say 25%, excuse me. And we want to select our ECM fans in the bottom 50% of the range. We want to limit our leaving air temperatures usually to no more than 90 degrees for overhead heating. We want to select our coils to meet the leaving air temperature or MBH requirements without exceeding the maximum GPMs by too much. We also want to deal with low water temperatures by using enlarged optional casings on our units. And we always want to install the units properly to ensure proper performance. So that's really the end of my presentation. I'm going to open it up to questions now.